All right, let's look at these structures here.
Look out.
Look at these structures and start see if we can figure out which of these are have the strongest interparticle attraction. Okay, which of these has the strongest interparticle attraction? All right, why would this have the strongest? Why would this one have the strongest interparticle attraction? All right, so this way of this way of symbolizing this is showing that what we have, and I meant to be COO2, okay? That's okay. Means this X down here means this is has an unknown number, almost an infinite number of covalently bonded structures, okay? And so this would be a covalent network structure, and that bonding, that sharing of electrons in a crystalline structure creates so much strength that overall it has the strongest interparticle attraction.
Yeah.
Not individually. Right. Between each COO2 particle and the next, that might be relatively weak compared to something else. But overall, the structure gives added structural integrity, you might say.
Right.
Okay?
Yep.
So this one is going to be the one that is going to have overall the strongest interparticle integrity structure.
Right. What would
Okay?
be the next one after that?
Well, why don't you tell me?
Let's see.
I'm not sure.
I would say PCl3.
Okay. What kind of interparticle attractions would PCl3 have?
Help me out, guys.
You have to analyze the formulas and say what's going on here.
Okay.
All right, so is this going to form a covalent network structure?
No.
I'm not indicating that with its formula, am I?
Right.
So what kind of covalent structure is it going to form? If it's covalent and it's not covalent network, what kind of structure does it form? What kind of particle structure does it form? What? No, this is a crystal. I heard somebody say it, but they're being really quiet back there. We're having some timid people here. Okay? These are both molecules here. Okay?
That's convincing.
Why wouldn't they get sick?
Everybody's covering their nose.
All right. Guys, folks,
Yes.
what did we talk about yesterday?
We need to keep each other
Oh yeah,
accountable.
that was yesterday. Yeah. Guys, you're going over the top. Hey, it's up here. We gotta get
All right,
that.
Brian, you need to calm down.
Okay.
Okay? Yes, sometimes you go over the top, and when somebody raises an objection, you're probably over the top.
Right.
All right?
Mhm.
The likelihood of you getting a cold
Very high.
from somebody breathing next to you is so low, it's almost inconsequential.
What's that mean?
That.
There's still a chance, though, isn't it?
Not sequential.
Folks, we need to concentrate on chemistry. But listen, even if they cough or sneeze, the likelihood of you getting a cold from that is very low. The way you most often get the transfer of cold germs, if you can call them that, from one person to another is through physical contact.
She tried to touch me.
Shh. Listen. So unless you're shaking hands or touching the same surface you touched, you're not going to get a
I'm
transfer.
gonna wash my hands real fast.
Now look, hold it. Shh. Please don't do that. You know what? I'm trying to help here, and you guys are just making it worse. Okay? As long as, even if you shake hands or touch the same surface, if then you go and wash your hands, you're pretty safe.
Yeah. Right.
Okay?
Because the soap kills the bacteria.
It washes it away.
Right. Just bam, man, down the sink.
So listen. Soap and water works even better than those, what do you call them? hand sanitizers, all right?
Really?
So look,
Kill 99 for Nick.
we're way off the track here on chemistry, but listen.
Listen.
I expect you to be more caring of other people than that, okay? If somebody's not feeling well, they're probably more sensitive than they would be normally. Okay? So cut her some slack, will you?
Sorry, Nisha.
You got to know when it's time to back away from that cliff face.
Right.
On
You
the
gotta
edge of the
put a
cliff.
sign there, you know.
All right, let's get back to this, please.
Let's do it. Let's do it. All right. Sorry, Phil.
All right, Ben. Guzman, Hudson,
Yes, sir.
y'all paying attention over there?
Oh, we're good. Maybe not.
Look, if you don't know whether this is more likely to be a solid or this has a higher interparticle attraction than this, you need to check your handout.
Handout.
It tells you that. It's got several pages of explanation over this.
Yeah.
Go back and study some more.
So we find the electronegativity.
You don't have to do that. These are different kind of particles. These are different kind of structures. Okay? If you aren't looking it up right now, what are you using your time for right now? Huh? If you're sitting there talking about other things or the weekend or your contest last night, Kaylee, maybe you need to be rethinking what you're doing here. Okay, are you wasting time? Are you preparing for the test? Or are you preparing to fail? Okay?
Failing to practice and practicing.
Failing to practice is practicing to fail. You have the opportunity to practice by looking at your
Don't
test,
listen to Hudson's quotes.
looking at your handout.
Today is the tomorrow you worry about yesterday.
In general, which tends to have the greatest interparticle attraction, metals or ionic compounds?
Metals because metallic bonding.
Yes.
What was the question?
Oh yeah.
Interparticle attraction.
Now, metals have a very wide range of interparticle attractions, but on the average, they have a stronger interparticle attraction than ionic compounds do. Okay? They have more structural integrity.
So it would be NiCO2, then Ni, and then PCO5, and PCO3.
Well, this would have the strongest.
Yeah, I know that.
This would be next, and this is third.
Why would that be stronger than NiCO?
It's metal.
But does it make it weaker at all? Combined with chlorine or whatever?
Doesn't make it weaker, but on the whole, the interparticle attraction that creates structural integrity is stronger for metals in general, on the average, than it is for these crystals, these ionic crystals. Now we're down here to the molecules, and that's what we have to figure out. Is it a polar attraction or is it a non-polar attraction? What's going on here? Okay, well, which one? Are both of them non-polar? How do you figure that out?
Wait.
Is that what you subtract from this?
How do you figure out whether the molecule is polar or non-polar?
The bottom.
Okay, so you got to figure out a molecular shape and you got to figure out polarity of the bonds, don't you? You remember how to do that?
No, I don't. I mean, I remember how to do it. I just don't remember.
All right, well, get out your test references. If you don't already have them out, shame on you. Test references, you need your periodic table of electronegativity. I need to know what is the electronegativity difference for a bond between phosphorus and chlorine.
Yes, sir.
What is the electronegativity difference for a bond between phosphorus and chlorine?
Oh, I gotta find my calculator. Tom would know.
Well, he did the math.
I couldn't find my calculator.
0.97. Is that a polar bond? Is it polar? I heard Tom say yes. Does anybody disagree?
It's polar.
Oh, Tom's already right. So I'm gonna go yes.
So 0.7 and up is polar.
No. 1.7 and higher is polar. I mean, is ionic. 0.5 to 1.5 is what we are going to consider in here to be the polar range. And that's between 0.5 and 1.5. All right, does everybody understand?
What unit was that chart in?
Unit 4, I think. Okay, so maybe you need to go back and review Unit 4. Okay. All right, so the only difference then between this molecule and this one is the shape of the molecule. They both have the same electronegativity differences in the bonds. So we need to find out the shape of this molecule and the shape of this one. How do we do that? We start with electron dot formulas. Okay. Phosphorus has how many electron dots? How many?
5.
1, 2, 3, 4, 5. How many dots do we put around a chlorine? 7. Now, if you didn't know that, how would you find out?
Look on the periodic, look what column they're in.
Well, that's a good place to start. That's good. Okay. So now we can do the sharing arrangement. And if I just have PCl3, then I'm sharing, or I have 3 bonds between phosphorus and chlorine. I have a lone pair of electrons up here. So then from there, then we're going to go to a Lewis dot formula.
Uh-huh. Banana.
And we could do a Lewis formula. We can go straight from this to the three-dimensional structure. How many sets of electrons do I have around that central atom? 4 sets. So what shape am I going to draw for 4 sets of electrons around a central atom? Tetrahedral.
Thank you.
And so this is a tetrahedral electron pair shape.
Yeah, man.
Okay? So from this, then, we're going to go and write, we're going to replace shared pairs of electrons with the atoms that belong there.
Right. You know what's ironic is it's called a pear shape and pear starts with P.
That is kind of ironic, isn't it?
Uh-huh. You know what else is ironic?
What's that?
An Amish person getting electrocuted.
I'm sorry.
Okay. All right. What do we do with this structure, folks? What do we do here?
Replace it.
Guys, we're trying to get ready for a test.
Erase the electron
Dots.
That is shared.
3 of them. So the 3 shared ones. Okay. So I'm going to erase those 3 right there, and I'm going to put chlorines on here.
Right.
And what's next?
Then you go to the next stage.
Okay, so I'll redraw this same drawing.
Then you gotta erase.
And then I'm going to erase just the lone pair. All right?
That's beautiful.
Okay. The question is this an even or an uneven distribution of polar bonds? We know the bonds are polar, and it is uneven.
Uneven.
Okay? So that makes this a polar molecule.
Right.
Polar molecule.
Smoke.
Okay? So that polar molecule then has a significantly greater attraction between that particle and the next one, this particle and another one like it, than one that is nonpolar. Okay? Let's see about this other structure up here, PCl5 then. We already know we have 5 electrons around the phosphorus. And we're going to have 5 chlorines. And each of those chlorines are going to have 7 electrons.
Mm-hmm. Mm-hmm.
And if I share an electron here, and one here, and one here, the only thing left to do then is to expand the octet and split up that pair right there. Remember, you only split pairs when you have to. Only when you have to. Okay? That then gives us
Y'all gotta do it right.
Show us, Misha.
a Lewis dot structure that looks like this. Okay? And then from that we can get our three-dimensional electron pair shape. And how many sets of electrons are there around this central atom?
That would be this many.
5 of them. Okay?
Right.
What arrangement, what is the name of the shape we're going to draw then?
Pentahedral.
That's yeah.
Oh, the
Trigonal bipyramidal. It's a 3-sided pyramid. Okay? And for that we're going to have one leg going straight up, one leg going straight down,
You got it.
one coming out here, but then over here you're going to have a set that looks like this. Okay? And there we put those electron pairs on there. And redraw that same drawing. Guys, calm down.
She been had the cold.
Calm down.
Guys, the level's up here. We gotta get back down. Come on.
Okay. Now what do I do, folks?
You erase it and replace it with chlorine.
All right. So all of those are going to be shared electrons. All of those are shared electrons. So I'm going to replace all of them with chlorine symbols.
So the other, okay, if they have an
Uneven
uneven distribution is polar, okay.
distribution is polar. Even distribution is nonpolar.
Right.
Okay. So what kind of distribution do we have now?
Pretty even.
That's even. So is this a polar or a nonpolar molecule?
Even Steven.
Nonpolar.
So then PCl3 would go before PCl5.
In terms of, yes. And if we're going to rank them as this being the highest here, then this is number 2, this is number 3, this would be number 4, and this would be number 5.
Right.
Okay?
Right.
With the highest being the one that has the overall greatest structural integrity, and therefore, or the highest, let's put it this way, the highest interparticle attraction as measured by structural integrity, okay? Yes?
If we had 2 polar or 2 nonpolar molecules, would you do it by the highest electron density? Would you go first?
Well, it gets pretty sticky there and a little bit beyond the scope of this class. I won't throw one like that at you. Okay, the question is, if I have 2 polar molecules, how do you figure out which one has the greatest polarity, the strongest polarity? And yes, electronegativity plays a huge part in that. But there's a lot of other structural things that go into that, and we're just trying to keep this class in kind of the basics. And so I won't throw one at you that makes you make that kind of judgment, okay?
Right.
All right.